Google recently introduced TurboQuant, a system that reduces the memory required for large language models by 6 times. But instead of easing the burden on hardware, this efficiency creates a textbook Jevons paradox. Cheaper AI inference costs are driving a surge in total compute demand, pulling even more chips into the system. That growing demand is colliding with a brittle physical reality. Right now, the prolonged conflict in the Middle East threatens to cut off the critical helium shipments required for global semiconductor manufacturing. This infographic maps the localized energy risks facing the AI supply chain. Looking specifically at the graphic on the right, Taiwan holds only an 11-day reserve of liquid natural gas. A localized power disruption would immediately halt operations at TSMC. The AI supply chain currently relies on the stability of global shipping lanes and highly localized energy grids. To bypass this fragile global system, buyers are taking direct physical action. Elon Musk is opting to build his own localized ecosystem. His $20 billion solution is the TerraFab, a massive new facility currently being constructed at a defunct power plant in downtown Austin, Texas. The facility's architectural goal is to consolidate logic, memory, packaging, and testing entirely under one roof. Engineers can manufacture a chip, test it, revise the lithography mask, and iterate immediately, without shipping wafers back and forth across the Pacific. Building a $20 billion vertical integration pipeline allows a manufacturer to function independently of a fragmented and bottlenecked supply chain. For companies relying on external production, the volume of compute required by the market currently exceeds the physical fabrication space available in the United States. Looking at this capacity forecast, TSMC's Arizona operations illustrate the extreme strain. The Fab 4 timeline indicates that their 2-nanometer A16 capacity is fully booked out to 2030, long before the facility is even fully operational. This shortage is compounded by a structural shift in the market, where the historical divide between logic and memory manufacturing is collapsing. SK Hynix is now utilizing TSMC's premium 3-nanometer logic nodes specifically to build the controller dies for their high-bandwidth memory products. With leading-edge logic capacity being directly consumed by memory products, access to advanced nodes is becoming a zero-sum competition for fabless companies. The friction extends to the price tags. DRAM prices have surged 80% quarter-over-quarter, driven by a structural inability to scale yield and advanced memory. High-bandwidth memory requires stacking multiple dies on top of each other. This three-dimensional integration introduces failure modes that do not exist in traditional flat planar memory. Engineers battle 3 microscopic failure points: alignment errors during hybrid bonding, thermal warping during stacking, and degrading interconnect reliability. Because these defects occur deep inside buried interfaces, traditional visual inspection tools cannot detect the hidden flaws. This yield crisis is creating pricing anomalies, where standard DDR5 margins are surpassing high-bandwidth memory, even as South Korean researchers push material breakthroughs to achieve 23 times faster 3D NAND array speeds. The physical limits of stacking chips and inspecting them in 3 dimensions now represent a greater bottleneck to scaling than lithography alone. To break this gridlock, the global equipment ecosystem is pivoting massive amounts of capital towards solving these exact 3D structural bottlenecks. The financial scale of this pivot is reflected in current orders. SK Hynix just placed an $8 billion order for 30 extreme ultraviolet lithography machines from ASML. Equipment giants like ASML and Nora are now aggressively moving into hybrid bonding machinery to overhaul the advanced packaging landscape. This chart tracks how these architectural shifts are driving the raw materials market. The precursor revenue forecast points to an 8% compounded annual growth rate through 2030, driven by the specialized chemicals needed for advanced deposition. The primary battleground for global semiconductor dominance has now migrated from front-end transistor shrinking to back-end materials and advanced packaging. Beneath the silicon and the packaging lies the primary bottleneck that cleanroom innovation cannot bypass: heavy electrical infrastructure. Micron's new fabrication plant in Singapore provides a clear example. Operating that single facility requires the installation of 500 massive electrical transformers. 500 transformers is more than double the global output capacity of any single manufacturer. To prevent thermal failure in these high-density systems, the industry is transitioning toward 800-volt DC architectures and heavy liquid cooling subsystems. The expansion of the AI economy is now tethered to the availability of physical infrastructure, specifically transformers, copper, and thermal management systems.